So let me introduce you the first speaker of today, the last day of this workshop, Arthur Lopes from Federal University of Rio Grande do Sul, and he will talk about Piecewise Analytic Subactions for Analytic Dynamics.
First of all, I'd like to thank the organizer for the invitation to give this talk. And the workshop is always very interesting, as usual. I'm going to talk about joint work with Gonzalo Contreras, Elismar Oliveira, and Daniel Ismania. And I'm going to talk about something that's a topic a little bit different from what has been talked here before, but inspired, the same ideas appears. The proofs are sometimes different, sometimes inspiring the same way. Well, to begin, I'd like to say that our setting is a compact metric space, an expanded transformation on this space, and MF will be the convex set of all invariant probabilities for this transformation. This is the general setting. Then in ergodic optimization, that is a kind of symbolic view of matter theory, you could say. You consider a space, a transformation, the space of invariant probabilities, and a potential. Initially, continuous potential, and we are interested in characterize the maximizing probabilities. That is, the probabilities mu that attains the maximum value among invariant probabilities for this potential A. One of these probabilities will be, in one of them, maximizing probabilities. Sometimes they are not unique, sometimes they are unique. And we denote by M of A the maximum value of this interval of all A. This is supposed to be like infimum of the Lagrangian among probabilities that are invariant for the Euler-Lagrange flow. This is just maximum, minimum, does not make difference here. Then we assume that we have a real analytic transformation of the interval that has a complex analytic extension to a certain neighborhood, has a fixed degree D, and you consider a potential that's real analytic and has an analytic extension to the same neighborhood. And we are going to define by mu infinity or mu infinity of A this maximizing probability, and you assume that this probability is unique. Not for everything, but in the end, you'll need something like this. And a natural question when you analyze thermodynamic formulas is that for each, if you fix a potential A, for each real value beta that we're going to make to go to infinity, we have an eigenfunction phi of beta that is eigenfunction for the well operator of potential beta A. And then one can ask what happened with phi beta when beta goes to infinity. And the real interesting question is 1 over beta log of phi beta. That's the same thing that you could ask for solutions of when you have a dissipation term like age Laplacian on the problem when you consider diffusion associated to certain Lagranges like Nannini and other, Diogo Gomes and other people. Then one interesting question is that what happened with the limit when beta goes to infinity? Then let's denote by V, in the case exists the limit of 1 over beta log of phi beta that's supposed to be something like a kind of subaction for the Lagrangian, but here we'll call the same name. Well, for results that we are going to prove here, we need some technical assumptions that was introduced before in a paper with Philippe and Elismar. That's a kind of twist conditions, because I like to point out, coming to the previous, is that different from the Lagrangian setting, the dynamic is the shift, let's say, or the transformation. This is independent of the potential A. In Lagrangian, the paths are solutions of Euler-Lagrange equations, and these are related to the L, that means the thing that you want to minimize. Then here, the situation is a little bit different, and then it's impossible to prove several results for oblimatic theory without convexity. Then in the rule of convexity, we have to assume some kind of twist conditions on the setting of symbolic dynamics. The while operator is the following. Giving a potential A, that is a transformation from 0, 1 to R, and you have a transformation, let's say Tx equal 2x mod 1, right? Then this x on C0 functions, this potential is C0, let's say, given a point x, given a function phi, you go in a function LA of phi, let's call psi, right? Then what is psi? Psi of x is the summation of e to the ai phi y, where ti equal x. That means that you take this point x, you take x1 and x2, the two preimages, and then you evaluated phi here, a to the phi here, right? And you are interested in finding the maximal eigenvalue and the maximal eigenfunction. Then we denote by phi a this eigenfunction associated to the maximum eigenvalue. And if I multiply by beta, right, I have what I'm calling phi beta. I'm just not putting the a because the a is fixed. Then as b moves, this function moves, right? Then you have the interval 0, 1, and this eigenfunction that is positive and periodic moves. You could wonder if this phi beta goes to something, but this phi beta goes to infinity or 0, moves a lot. And what makes sense is to ask if this converges to something. I'm going to give more precise definitions later. I'm just giving the basic idea. And it's known that there exists a real analytical eigenfunction which has here is phi beta is defined. Is real analytic here and has a complex extension to this neighborhood. And what you like to know is that what happened with domains of analyticity of this when this moves. Maybe when t beta goes to infinity, this could create some pinches and destroy the neighborhood. Right? This is a natural question. And just to put this in perspective, these operators are introduced by Well, Sinai, Boeing, and other people. They're supposed to be the basic tool to giving an interaction given by a function A. And if beta is 1 over temperature, this is a way to give the give states associated to the potential A at temperature beta equal temperature T, that is 1 over beta. This is the, but this is good works well just for spins on Z, not on Z square. On Z square, you have to consider actions and not transformations. But there's a big theory about this. And what you want to know is that what happened with this. Well, the main theorem is that this, if you assume that this maximized probability is unique, has support in the periodic orbit. This is a strong assumption because, but In most cases, the maximized probability is a periodic order, but there is examples that are not. F is analytic, order preserving, is just not very important, the assumption. And the function A, that's complex, is generic. The result have to be for generic A. And satisfy the twist condition that I'm going to explain later. The twist condition is a property of A, is play the rule, let's say the Lagrangian is convex in some sense. Then this limit exists, it's already known, and it's piecewise analytic, it's not analytic in general. Unless you have just one periodic or one fixed point, and then it can be periodic. Then I'm going to explain the proof, and I like to point out that we have some assumptions. That this is to say that in the general case, the problem is very complicated. This neighborhoods can make crazy things. We put a lot of assumptions, and even though they have this behavior of shrinking and pinching and maybe destroying the domain analyticity in such a way that they are piecewise analytic. There are already examples by Bush where he has a potential that's analytic, and this potential, the subaction, V will be the subaction, is not analytic. But what I'm going to show here is the mechanism, why this happened, give explanation why this happened, and we're going to use basically ideas that are inspired by sobre matter theory. Okay, then let's be that. A subaction for a potential A is a function that satisfies this equation. V of x minus V of x bigger than A minus MA. This is a kind of subaction that you have in continuous time. This is a discrete time version of the subaction that you find subsolutions of Hamilton-Jacob equations that we have in sobre matter theory. Then we say that this subaction is calibrated when we have the property that suppose F is 2x mod 1, then you have two preimages. Then we have an inequality, but the equality has to be attained in one of the preimages. I mean, one of the points I, that O and X, have to be equal the subaction equation. Calibrated subaction is unique up to additive constant if the maximized probability is unique, like in matter theory. And the subcohomology equation means becomes an equality in the support of the probability, but could be positive outside. We could have an equality outside the set. What I'm trying to say is the following: if here is the interval 0, 1, and here is the support of infinity, we consider the R of x, that is the error of x, that is this difference. I think it's this. And this R function is 0 here, but could be eventually 0 outside the support, and this equality could be, this is not generic, but it could happen, and this can create problems. This is useful in the sense if you know M of A and you have an explicit subaction, we can have an idea where the support of the probability is. At least have to be contained on the zeros of this function R. That's a mistake. The equality can be true outside sometimes, but it's not generic on A. Okay, then we're going to use some results that we considered before that can look a little bit this transformation don't have to be 2x mod 1. Here is. Then here's the transformation T, the graph of T. And in our notation, we are calling phi 1, this inverse branch, and phi 2, this inverse branch. Then we have to consider a system that is, in the case you have two elements, will be the symbolic space this is what we call omega hat. And these are symbols that will be associated to the use of this. In some sense, we need a natural extension of this transformation, which is symbolic in the symbols, 1 and 2, that are the inverse branches. Then, in this space, we define what will be some kind of natural extension. That is, omega is always an element here. And x is always an element here, 0, 1. Then we have the usual shift in the space of Bernoulli 1 over 2, in the case we have two branches. And this is a kind of natural extension. Then you apply the shift, and then you apply the first symbol that you have in the omega 0 to take the inverse branch. This maybe does not look natural, but we have no idea how to prove the result that we want without using this machine. Then, giving a potential A holder, we say that A star is the dual of A if there is a function omega of W and X, which we call involution kernel, that satisfies this cohomological equation. But you see that now is for the natural extension, is not for the initial transformation. This omega is better to look like here we have the interval 0, 1. And here we can think in binary expansion of this. Then in my picture, this is omega, and here is x, and here is omega x, or x omega. Does not matter. That means we have to go to a symbolic of the branches of this to be able to do. Then, okay, let's step as a definition. Given A, we have A star that is the dual if there is a omega like this. Just to give a flavor why you have to do that is that in the case you have a potential on B not on sorry. Suppose our system is this, not this. When you are working with maximizing probabilities, there is some things like in open matter theory that you have to go forward and backward in the Lax-Volenic operator. Then you need to have a sense of going backward and forward. And then this A, if this A depends just on two coordinates, the A star will be the symmetric. Then it's a kind of dual object. But when this depends on infinite coordinates, what will be the symmetric? The symmetric is A star. If transformation F preserve orientation, then on the symbolic space, shift times 0, 1, we can obtain this A, that's a function. A star will be a function. Here, and A is a function here. Then we have to consider the dual space. F is the transformation. I'm sorry. F is the transformation. I'm sorry. Sometimes you use T, sometimes you use F. F is the transformation of 0, 1, and then you take something that extend you acting on the branches. I'm sorry.
Oh, do you have some restriction in W? If you take W equals 0, then you can just...
No. You're giving A star exists if there is a W. The W is given together.
Yeah, but why don't you choose a star equal A composed with sigma hat minus 1 and W equals 0?
A is a function defined on the Bernoulli space, and A star in the Bernoulli space, A is in the space, and you have to consider the sigma minus 1 that mix backward branches.
No, but you say this object, the lot of objects exists. Why don't you take W equals 0 and define A star by the equation?
But A star have to be dependent just on Y, not on X and Y. Sigma hat is a function of X and Y.
So what does it make sense? A equal sigma hat minus 1?
Sigma hat depends on W and in the point X. This will be
So what is A composed with sigma hat minus 1?
this is A, right?
So again, why don't you take W equals 0 and just take A star?
A star is homologous to A, but it depends only on one variable.
Oh, okay.
It just depends on W. And I wrote A depends on X and W. This kind of things appears in Boeing when you try to obtain something homologous.
So you don't start W at the same time?
Yes, you have given A, you have to find A star and W, and there is some abstractions to do such kind of things depending of being preserving orientation, not preserving orientation. There is technical thing, but because this is one of the reasons we have to assume that FG is preserving orientation. But then you can do this by the other way, changing what you call the shift. It's true that the maximizing probability for A and A star are the same. Then you have, given A, you have a dual object that if A depends just on two coordinates, will be the symmetric of the matrix. But if A depends on infinite coordinates, you have to looking backward, and this is the A star. Okay, then here is the definition of the Ruel operator. Given a potential A, you have this action. And by the way, I like to point out this for people that are not very familiar with this, that the name of Ruel operator, sometimes people call Perron-Ruel operator, in the sense that if my potential, let's say B is defined on here, but suppose that B depends just of the first two coordinates, then it's not difficult to see that if you consider the shift of x0, x1, x2, xn equal x1, x2, xn as usual, this equation here is nothing else than a matrix, because it depends on two coordinates, and the existence of lambda is the theorem of existence of solution of Perron theory for positive matrices. Okay, then this is the definition of the Ruel operator, and you consider the action of LA star acting on the dual space. You have a new potential on the variable omega in this Bernoulli space, and now you take the pair phi and phi A star. These are the two eigenfunctions associated to the same eigenvalue lambda A and the 2 Perron-Frobenius operator. For people that are familiar with stochastic process and Markov chains, there is a usual way that if this is a paper by Spitzer, if you have a potential that depends on 2 coordinates, you can transfer this potential in a Markov chains, and you have to use the left eigenvalue and the right eigenvalue, and the left eigenvalue and the right eigenvalue correspond to phi and phi A star. That you have to put together to create the pi, and the pi is the initial invariant distribution. But in infinite dimensions, the dual of functions are measures and so on. And then, but here you are having function and function as dual, not functions and measures. And we'll call nu A star the eigenprobabilities for the dual operators. Then answer the question why these operators are useful. I just point out the following, that we define the well operator as I just mentioned, and you look for this, and you take the dual operator acting on probabilities, and you have the same eigenvalue, and if you consider phi nu, let's call this mu, this is a function, this is an eigenprobability, and this is a probability. Then what Ruel, Sinai, and Bowen consider is that if you are interested in maximizing entropy plus a potential, like in statistical mechanics, a Gibbs state is a probability mu, let's put here, d, mu d, such that realize the maximum of the, this is called the pressure or large deviation in some context. And then a Gibbs probability is the one that satisfies this. Then if I put d here, d, 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 this is the solution of the pressure problem. Then when you put beta here, you have a beta in everything. This beta is like 1 over temperature. Then when temperature goes to 0, this became big, entropy is bounded. And then this makes that this mu beta d, when beta goes to infinity, converges to mu infinity d. That's the reason to put infinity here. And we assume that this limit probability is unique, then this convergence is a really convergence. We converge. Then if we consider a real potential A fixed and mu B, then this Gibbs states mu B, mu beta A will converge to the maximized probability. Same thing for mu beta A star, and this converges to maximized probability of A star. Then, as I said before, here we are analyzing thermodynamic formulas at temperature 0 because beta is 1 over T. This is a way to look at it. And generally it is supporting periodic orbits, but has to choose a special space of Holder with a certain norm. A Holder norm with a special different way of looking. Then we choose a normalization because we have nu A and nu A star, the two objects, one acting on X, the other acting on W. C is just a normalizing. Calibrated subactions exist and can be obtained like this, the same way like in matter theory. And you have the V star that's calibrating for the other one. And this is the interesting result that you have two objects, and the dual of probabilities are functions. And then this involution kernel plays a role of an integral operator that, when integrated for h omega respect to probability nu of A of x, you have an eigenfunction for phi A star. And if you take the integration with respect to nu A star, you have the eigenfunction for phi A. This will be essential for what we're going to do, these two equations. Because we have to consider large deviation properties. What are large deviation properties? Large deviation properties is a natural thing to consider that is the following. Let's suppose you have the interval 0, 1, and you have here in yellow the support of a limit measure, let's say mu infinity of A. And we have Gibbs states. Let's say like a Gibbs state to be something like this. Mu beta, that's a probability. That's the measure of this is this. And suppose that mu beta converges to mu infinity. Then we imagine that for big beta, the probability will be something like this, right? Okay, but then you could ask, suppose you take a small interval here, AB, outside. Then mu beta of this interval, AB, goes to 0. But you like to know the speed, the velocity. Then you like to know 1 over beta log of mu beta of AB. This is what? This is supposed to be a negative number. And you said you have a large deviation principle when you are able to find, let's see this picture here. When you have a function I that has this strange property. It's positive, is 0 on the support. I make a nice picture because this I function that I'm going to define can be infinity in several points, but it's lower semi-continuous. Then large deviation principle exists when you are able to exhibit a function I such that this is infimum of I of x for x in the interval AB. The name of large deviation is because this is not a set that you're going to see, but you like to see to say that your probability goes fast to this one, in the sense that the probability of a set that is strictly outside. Let's say, let's put the interval AB here. Then the infimum of the function Ix on this is this number, which is positive. Let's say is 0.7, this number. Then this is minus 0.7. This said that the probability of AB is going to 0 like E na minus 0.7b. And this goes exponentially fast as far as this is positive. Unfortunately, you have to say what is exactly the I. And in our case, when mu beta is the Gibbs state for beta A, that's the I. See that you are making a summation on the orbit of the point X. And see that V composed with F minus V minus this is positive. This is the R. This is always positive. And this is 0 when you are in the support. Then, if here is the support, let's say it's 2 points, 3 points in the periodic orbit of period 3. You have other points here, X. Then you are taking R of X plus R of F of X plus R of F2 of X, and so on. If you begin here, as this is invariant, you are always here, this R is always 0, then in the support of probability, this is 0. But unfortunately, there exist counterexamples where I can be 0 in a point that is outside the support. Let's wait here, the support. And this is something that has to be deal to our problem. Anyway, the deviation function is this, and this is true for any interval. And you can apply this for A and for A star. You need both. And E star is the subaction. That means is the speed of velocity such that this probability goes to 0. Is the infimum of this. Then probability mu beta goes to beta, and the large deviation principle is true for this I. And this was proved before, and this I is important. And as I said, I can be 0 outside the support. This is bad. Okay, but this can be seen as a problem in transport or transport on the space of probabilities. This is the equation that you get from transport and the support of a probability that's in the omega x space. Then we have this probability also for the A star. Then this is a kind of strange because we want to consider something for a transformation F. And we are going ahead and look for the symbolic of the branches for some way. This will disappear, but we need a proof, and you see why it is. Okay, there is an evolution kernel, and what we're able to show is the following. Now we came to the basic point that is the following. Here is the first part that we need is that this evolution kernel is such that for each omega 0, omega, that I fix, this function here is analytic. That does not make sense to ask anything about the variable omega because omega is in the shift. But for each omega, this can be shown to be analytic. Then we need here the Vardan theorem. Vardan theorem is a kind of Laplace method, but instead to have the function dx to integrate it, you have a special measure, mu beta, that always also changes. And then this is a general theorem by, well, a lot of people don't know. That says the following. Suppose I is deviation function for the family mu beta converging to mu. Then you see there that this mu beta is moving with beta, and the b that you put there is moving. If mu beta, the measure does not depend on beta, then the Laplace method would say that just you have something related to the supremum of the function g that you are putting there. But as you have a probability, you have taken account how this shrink with beta. And then is where the deviation functions appears. That's the reason why you need the E star of W there. Okay, then, now you're going to see why you need this deviation function, because this already appears in some other papers, but you see. See the first expression. The first expression comes from the property that we show that these involution kernels transform the eigenprobability for this potential in the eigenfunction for this. Then we need to put mu beta A. Then you have to divide and multiply by phi beta. Because the probability mu beta A is phi beta A mu beta A. Then if you add and subtract, add and put 1 over, that's what you put here in the first expression. You put phi beta A star I minus log there. Why you put there? Because then you have mu beta of A, and then you put the beta outside everything, and this will be something like a G for us. And then you can try to use the Varadhan theorem. Then you use it, and the expression that you get is this one, that gives you the transformation Vx that is a subaction for A as a kind of Legendre transform of V star, that's the subaction for the other one, when you use this spatial W omega x minus I. That's the reason because the I is necessary, I star, when you use the Laplace method. And then we are almost in the end of the technical points that you need. Because you see that given x, you maximize in a compact space the space of symbols, then you are going to find out omega x, that's the point that maximizes this. For each x, there is an omega x. But for each x, there is an omega x that realized, that supremum is realized by omega x. Then we need some control of Wx. And the proof goes like this. Suppose that if omega x is locally constant on x, then you do not move the I star, you don't move V star that you don't know what it is, and you just fix the omega x and just move x. Then if omega is locally constant, then this is analytic on this neighborhood, because for each omega we show that as a function of x is analytic. The point is how this can change with x, the omega x. And then, okay, to be sure that this is piecewise constant, we need to control something that is a little bit delicate, is that you see that omega and W are continuous functions, they are bounded, but E star is not bounded, can be very, very large. But then you take out the points that I are very large, because if I is very large, this probably will not be a point that you're going to be the supremum, because you're putting too many. You take the supremum of omega x plus V star, then this is a bound that anything that has I too much high will not be the solution. Then in this way, if you take this, you can say that given a certain k, there is a finite number of omegas such that E star of omega is bounded by k. This can be a problem if there is a point here that is in the preimage of a point that is in support of mu A star. If this is 0, this is a problem. But we are looking here for the deviation function for E star, not for A. It's easy to move A and make the E of A is not 0 on that point for a potential A. But for E A star, this is complicated. Then we need a generic result, and one of the statements of the paper is that generically on A, not on A star, the I star of A is not 0 outside these preimages. then the I here is positive in each one of the parameters. And this makes that anything that has spinning around here each time goes out have to be some I. Then this makes that the number of possible omegas are finite. And then this is the reason why we need generic on A. Remember that A is a function on X. Then the potential here has to be generic. And then the A star will not have points with IA star in the preimage 0. And then we'll make that there is just a finite number of omega x that can attain this supremum. Even though if you have a finite number of omega x, I'll make here the picture. Here x. You have just a finite number, but you could have something like this. You could have jump. And then if you assume the twist condition, you consider the lexicographic order on the shift, then the twist condition is the following. Given A and B here, A prime, B prime here, here is the Bernoulli space with the lexicographic order. Here is 0, 1. Then G is twist. If G of A, B plus G of A prime, B prime is smaller than G, A, B prime plus G, A prime, B. That means that if you add these two guys, this is bigger than if you add green is bigger. This is a kind of twist condition, and with this condition, this function omega x will have to be something like piecewise constant. And then for each x, you have intervals where omega x is constant. If omega x is constant, when you move x, this will be piecewise analytic. And this proves the final result using this strange way of looking things backward. And the claim has nothing to do with the backward machinery that you use. The claim is that if the maximizing probability for a potential A, real analytic, with an analytic expansion, has support in a periodic orbit, if F is analytic, order preserving, the analytic function A is generic and satisfies the twist condition. I point out that twist condition is for the potential for omega. We say that A is twist if the corresponding omega is twist, in order that when you maximize, we have this omega x is constant by parts. But I point out that this is a property that you check just for A. You do not have to know explicitly W. It's something that you check just looking A. And then with the twist condition, we are able to show that you have a finite number of omega x that are possible, and this omega x give you the intervals where you have to fix the analytic function associated to omega x as a function of x, and this shows that this is piecewise analytic. And I finish here.
Are there questions or comments? Okay, so let's thank Arthur again.
Obrigado.